transcribed this and put it as a document in the proceedings. No idea where it's going to go or if it's going to go anywhere, but just have some fun and don't even know where to start. We should have somebody have an opinion on what the most challenging parameters of the model are, that we can argue some of them out. And you know, like they say, that took Solvay 15 or 17 years, so it's going to be an ongoing project. And we want to submit a proposal to NIST, primarily because they have all the equipment. And we had some people here at Morgan State who've been on the staff at NIST and did the experiments at NIST, so we have a little bit of help here to...
You can start by explaining what ham is.
Yes. Ham is an insult to Lou because he's of Hebraic origin, and you know, and his name. HAM stands for Holographic Anthropic Multiverse. It's I couldn't do the static universe because that was debunked. The Narlikar-Hoyle, I didn't stay with that term because they incorporated inflation or expansion. So I came up with, I needed the term anthropic because of the, I also...
Got to spell hand correctly.
So why don't we use
H-A-U.
the microphone?
What's this for?
that for?
Well, if I'm whispering too low, then...
I'll do it and talk to you, Tom. Hey, Tom! This is your conscience speaking.
Anyway...
Is the official...
Okay. Set up in some central point where you can kind of see, pan back and forth a little bit if you have to. So because I think there's, following Descartes, that there's a res cogitans in addition to res extensa, which is not popular in the physics, still has only barely begun to address the role of the observer. But following Descartes, I wanted an anthropic principle, an anthropic cosmological principle. Holographic, you can also get non-locality out of that. Multiverse is self-explanatory, maybe it's somewhat theological. Grains, worlds without number have I created, like grains of sand in the seashore. And I follow the Vigier and colleagues' model of tired light, where Hubble discovered redshift, not expansion of the universe. And they're in certain models of the Dirac vacuum and extended electromagnetic theory, there is good reason to suggest that there is an alternative to the Big Bang. As I said in the lecture, there are key elements of this particular holographic multiverse, and the essential ingredient is the structure of the least cosmological unit. There is some vague precedent for that, where I noticed really only one paper, primarily a volume, edited volume by Kafatos, he may have had a co-op, I don't remember, where one of the authors talked about the size of the least unit, and he ended up having that be very close to Planck, which is what you would suspect for the standard model. The Planck's stochastic virtual foam is the basement of reality. But, one thing I forgot in the lecture, most physicists believe that the extra dimensions, if they exist, are Planck size because we don't observe them. If you use a form, if you model your arrow of time with subtractive interferometry, imagine a movie theater model is best for this. You have the discrete frames of film at the projector, and then reality is continuous. And even a few centimeters per second is too fast for our vision. And the model of real reality is relativistic, and we're embedded in and made out of this material. So one metaphor for this is the two forms of screen animation. One, you have the little stick figure standing in the center of the screen, walking, in the background is moving. The other one is the background is fixed, and the stick figure goes off stage right or arbitrarily and appears back in the other one. And I think that kind of duality actually exists in this model. But you add a subtractive interferometry to this because we're relativistically, because we as observers, all of that we perceive is coupled to free space. And so at the point when you're going to see something else, it's subtracted out, like the frames of film in a movie, old-time movie theater. You don't see between the gaps. The main requirement out of the multiverse is this continuous state. That is essential, it's key. And the thing that is just as key is that in the hierarchy of dimensionality with its continuous state, spin exchange, and dimensional reduction compactification process, that's the mantra of this. When you get down to near the 0th dimension, asymptotically, never quite reaching it, the Riemann elements of the least unit flip back to infinity. So all of this, I know it's very complex, and I've been very poor at putting this together in a more rigorous way, but that can be done as we go along. But part of all of this is just to me it seems essential that we understand conceptually so that we know why we're using the resonance hierarchy to look for there were no hidden cavities, QED cavities in the standard model. So we surmount the uncertainty principle to find the little periodic cavities that come in this model into the pockets of the higher dimensions, and they're limited because, as we talked about at the end of the presentation, uncertainty is a manifold of finite radius or finite dimensionality. And Elizabeth helps us refine that. It's probably going to be 4, 5, and 6 dimensions. If the way that a second doubling of Peter's space anti-space occurs, it may have 9, but the redundancy may or may not still mean there's only 2 or 3 new spectral lines. We must, in conjunction with the continuous state model, it's the only way to surmount uncertainty. When you surmount uncertainty, we did review how, with the Stern-Gerlach experiment, arbitrarily, we set out the continuous field along the z-axis. We get, as empirically demonstrated very well, we get the Copenhagen quantum uncertainty principle. So the key was to do something else. It has to be in a setting, which the complexity of it to describe it, it's a polarized, conformal polarized Dirac vacuum. When we add M theory to it, it also has a scale invariant copies, mirror symmetric copies of whatever the piece of matter is down here. And as we tried to explain, because of the creation, annihilation, and the boost from superluminal Lorentz boost from space to time to energy as part of extending, Bohm and de Broglie-Bohm failed. They didn't work very well in 4 dimensions. But if you extend it to 8 dimensions or so, you can complete quantum theory in that sense. Kramer marginalized, both of these have been marginalized either because they perceive that they don't work, they don't add anything new. Kramer is marginalized mostly because they don't think it adds anything new. But this standing wave of the future past for a Kramer transaction aligns beautifully with the continuous state, especially as it applies to Calabi-Yau mirror symmetry. So that's why I start the foundation of this model with Kramer. And as most of you know, Kramer derived his model from the Wheeler-Feynman absorber theory, which also didn't quite work in 3 or 4 space. Then we mentioned that to do the experiment in terms of the Dirac polarized vacuum, which is susceptible to, it has maybe one end of the continuum is the Dirac polarized vacuum, the other end is the Einstein energy dependent spacetime metric. use the difference in definitions to talk about different things, where Einstein is talking about warping and bending space-time and the energy that's associated with that. But at a different scale or a different way of talking about it, you talk about the Dirac polarized vacuum, which is susceptible to electromagnetic interaction under certain. As I mentioned, the primary evidence for a Dirac polarized vacuum is the Casimir effect. The lesser indicia are the Zeeman and Aharonov-Bohm effects. Because extended electromagnetic proponents have also talked about tired light, it has been perceived to interfere with Gage's theory. That's actually a misnomer. Gage's theory is an approximation suggesting there is new physics. And in any case, that it can be shown easily that it doesn't interfere with Gage's theory. So then we take the Sagnac effect, counter-propagating laser beams interfere in the small scale such that they interfere with special relativity. We take the Dubois incursive oscillator in conjunction with the Sagnac resonator. The size of delta T in the incursive oscillator can be the size, the bandwidth of the hole we want to punch in space-time, which we would correlate with the rest of the experiment. We're using hydrogen, so that has, the other thing I didn't mention, I have a tendency to believe in, until you take the measurement, you have the Schrodinger alive dead cat. There's nothing going on, so until you take the measurement, it means that you can take the measurement and do whatever you want to do. It means you can, whatever atom or structure you use to apply a field to, you're going to get results based on that. So it's not like you have to use hydrogen, you have to use titanium. You can do the experiment with whatever atom or molecule you want to do. Hydrogen is the simplest, so it's going to have the least artifact to hide it. And so that's the one you pick because it's going to be the simplest way to do the experiment. The Bohr orbits were the simplest, and then they discovered other ones, and then there were refinements. They originally assumed that the nucleus was fixed, rigidly fixed, and then they noticed that there's going to be a little wiggle in the nucleus, and so there are refinements to these spectral lines. As I also said, I think the best indicia that we can have this kind of violation of QED is from the NIST experiments. Not all of Chandler's experiments were done in NIST, just the most recent. The original ones, I have to verify to be sure, I think he did the original ones in hydrogen, and there was a suspected violation of QED, quantum electrodynamics. But it was too small that the physics community essentially ignored it. In 2012, and I just think that's the cleverest thing, to take a larger atom like titanium, strip all the electrons off at once, so and essentially you have a large hydrogen atom with one electron. And then, assuming that the uncertainty principle, you try to measure one thing, as soon as you touch anything, it decoheres and collapses the wave function, or makes it evolve to another state if you're going to do. And I didn't read the experiment very well, I haven't done it for a while, to whether one pulse or what you do, I suppose, if you just do a pulse and get your reading back as a cross-section of however they did it. It doesn't make a difference for how long before you do the next one. But because the titanium atom was so much larger, there's more space to collapse through. So that's why the artifact was large enough that the experiment was perceived to be much more successful. And there were, of course, some whispers then, Nobel Prize. But of course, it's still not dramatic enough. Still, most 80% of the physics community still is skeptical. And that's the way it always is in the history of these things. But that is the best indicia that we can find new spectral lines in hydrogen. The fact that people at CERN are looking for them in a different way, they haven't started doing the experiments yet. That's just other people looking for higher dimensions. So to repeat, in conjunction with hydrogen, You set up your RF pulse, Sagnac effect, incursive oscillator resonance hierarchy to shake the electrons. And I would guess you're going to shake the electrons in some way no matter what frequencies you use. So we want to shake them so that they resonate, they do some kind of spin coupling or spin orbit coupling with the nucleons. Then, and this is one of the things that remains that we haven't do, we need to figure out, and I hope the algebra will just make it fall into place, what is the size of the least unit? And that will give us the beat frequency of space-time. There is no beat frequency of space-time in the standard model. This only applies to this continuous state cosmology. There's no need to even look for a beat frequency of space-time and reduce it to a plane as the basement of reality. You could try to maybe do something with the Zitterberg-Wagon or virtual particles to see if there's some kind of quantum oscillation, but we have a different kind of beat frequency in the rotation of these Riemann spheres. And since they're close packed, you've all seen the little toy where you have some little magnets on pins, and you take another magnet and bring it near it, and all the magnets jump around. So we're going to set up, according to that metaphor, we're going to set up, so the least cosmological unit is not one magnet on a pin. It's an array of however many figure out we need to close back. Then we will finally, the final level of the experimental tier is our electron-nucleon resonance coupling must be done also in conjunction with the beat frequency of spacetime. And because there are some papers, there is a lot of work on cellular automata and programming the vacuum, I also think that if you apply some bandwidth to the vacuum, because of the infinite potentia or the way that this can work, the close packing, the geometry of the close packing is such that any bandwidth will have some effect on the tessellation behind the vacuum. So I haven't looked yet, and maybe Elizabeth knows, nobody essentially knows how to couple the lower one to the space-time tessellation, but something about electron, nucleon, least unit, tessellation in terms of this hierarchy with the incursive oscillator especially. We'll open and close. We will have, because, as I mentioned, the inherent hierarchy of this continuous state, because of an anthropic principle, or I think you can get around that, I just haven't done complete thinking of it, something about how matter is created. If we're going to have, we don't have a full handle, we haven't girdleized sufficiently that we're outside of what a particle is. But with the unified field, we'll be able to girdleize outside of what a particle is. So we'll be able to observe the full creation of a particle. Right now we have just the tip of this iceberg in Minkowski space. So again, just to summarize and try to get out of this infinite loop that I'm getting into. In that sense, the experimental design is that simple, based on these cosmological premises. Shake the electrons in conjunction with coupling to the nucleons in conjunction with the least unit rotations, timed with an incursive oscillator. This is in some of the books. You know, I'm just glossing over things that have a fair amount of complexity that they need to be rigorously reviewed and understood. We will time the incursive oscillator, and this, because of the inherent, this continuous state dimensional reduction, blah, 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 hierarchy, that's something that's going on behind the scenes all the time. It's inherent in this cosmology. And with the movie theater, we don't see it because it's relativistic to us as three-space observers. But because it is inherent in this process, we're getting half of this experimental design for free. It's built into the cosmology. So all we have to do is tack our, Feynman called this, when he first said how to build a quantum computer, he said use a synchronization backbone. People tried to do that, but they decided it was tractable because what they did amounted to bilateral. They were still doing it in four space, so they take the line element and do something in this part and this other part. They didn't get a real synchronization backbone. But there's an inherent in this continuous state structure a synchronization backbone. So it makes it so much easier to open the resonance hierarchy. So the RF pulses have to be timed when the gate is open, increasing, as we said, here's the lowest Bohr orbit, so we'll call it radius R. And then when you have the gate open, you're going to get R plus delta. And that R plus delta will be a slightly increased cavity. In the lower, we mentioned the first Bohr orbit is half an angstrom, the second one is 4 times further out, 2 angstroms. So we're going to get a 0.6 angstroms, 0.7 angstroms. I haven't done the calculations yet. Using the higher dimensional volume formula, it's too simplistic, but that will give us a good approximation. I'm pretty sure there'll be refinement. So before we submit, and this is work that any of us can do, is to finish calculating the volume of those orbits, which will give us a lamp to give us a wavelength. And then we will have to apply a Bessel function or something to the algebra to get the other. The beat frequency will tell us, if it's femtosecond, nanosecond, how the opening of the hole in space-time. But anyway, then simplistically, periodically in this continuous state hierarchy, the cavity opens, so we send in our RF pulse, and it's reflected back into the NIST spectrometer, and then we will have a verification of what the wavelength of those spectral lines is. Hopefully that was a good overview. If there's a gap or something that's not understood, please ask a question. If not, I'll pass the microphone to other people.
Okay. There are lots of terminologies which I would like to have explained. I'm going to just list them and then we could maybe start at the beginning. Least cosmological unit. Duality relationship between foreground and background. Dimensional reduction process. Resonance hierarchy. Cavities in the pockets of the higher dimensions. Uncertainty as a manifold. Mirror symmetry in this context. What means the rotations of the Riemann spheres? What is the beat frequency of space-time? That's perhaps enough, but you see there are many aspects of terminology which sounds very enticing, but for which I do not have any attached meaning, and so can't quite follow the form of the large-scale picture that you're drawing.
Okay, so tell me what's the first one on the list again?
Yes, talk a bit about the least cosmological unit.
All right, this, other than the hymn cosmology itself, the least cosmological unit is key to the whole thing. Without that, we have nothing. It's just it's a theory that can't go anywhere and has no meaning. In the history of my development of these ideas, some decade or so ago, I came across Kapatos's book where one of the authors, it's in the Ham Cosmology, which you have a Ham textbook, which you have a copy of. It's not a textbook, sorry. Reference to that paper and a little discussion of it. He came up with what he called the least cosmological unit, and he said its radius was the Planck unit, Planck relative. I think he might have added a small little factor for oscillation, but it was essentially a Planck unit. I periodically looked at crystal structure, and they have let's see, what do they call the least crystal unit?
Unit cell.
Unit cell, thank you, Peter. The unit cell. One unit cell builds up the whole crystal structure. So this terminology is somewhat arbitrary. I needed to have terms. I tried to have them correspond a little bit to existing terminology. but there is no such thing as a least cosmological unit in the holographic sense. So then, in order to move towards the beat frequency and the rest of it, and have a space-time vacuum that can be programmed, that can have cellular automata, this, as I mentioned, the simple drawing, which interestingly is like the logo for cross keys. And I tried to explain, we have in the center of it a vertex. That part should be okay. It's not just a standard model vertex, but we put the Witten string vertex in the middle because it adds that extra dimension, but gives it a chance to wiggle.
When you say a vertex, you mean a fundamental interaction?
Do we have to say a fundamental interaction, Peter? If we have a fermion?
That's what I understand it to be.
All right.
I mean, a vertex is a point where you do have
All
such
right.
an interaction.
All right, but I could alternatively just talk about it in terms of metric.
Well, I'd say it requires an action. In
Okay.
other words, it's a change from one state to another. However, normally it would be used in particle interactions, but if you had a fundamental space-time structure, it could be a change in structure of that space-time.
So I can get away with this by just saying it's the stochastic quantum phone that's the background of the standard model, and that would suffice, yes?
Suffice for him.
Well, I don't think that's what you mean
Yeah.
then.
Well, no, we can't throw away physics. There has to be...
No, I'm trying to understand. You see, what you said, Capado said, is what I said in the early 70s and the late 60s, that the quantum foam is a Planck size. That wasn't accepted at that time. But you can quantize space and time, as well as matter and energy and so forth. And like in the Lippmann-Schwinger equation, the independent variables are P and E, rather than X and T. So you can talk about a fundamental, Ilya Prigogine did too, a fundamental structure that is a discreteness at a very, well, I say at the Planck length, that is a quantized of the space-time vacuum, I mean reality itself.
This is important because can we say in empty space, say between galaxies or something, there's no, where we consider that there's essentially no matter, there's no, do we have to have, so the consensus among contemporary physics is unless there's some matter or interaction there, you don't have the vacuum, you don't have a, we have a
Well,
planet.
the way I would
Yeah,
look at it
right.
is this. In order to make a measurement, a space-time measurement, I'm measuring space, so I have to bring up a ruler. I have to do a process of bringing up my ruler to measure this space. That takes matter and energy. And to run a chronometer to measure time takes matter and energy, probably a battery. So I don't see how to separate space-time as a fundamental reality from matter and energy, and that's what's in my presentation, that I treat a bunch of these variables as degrees of freedom or dimensionality. And so that they actually have to all exist at once. I can't have empty space and empty time because I can't tell it exists, and I can't have matter and energy without space and time because it has to be in that arena, as Wheeler would put it.
I think it's okay if we, as I like to assume, have a space of infinite potentia in the background, and it's all nilpotent, as Peter suggests. It could be doing nothing until we do something to it. So in that, I think I can get around or have that suffice to say that there's an infinite potential, and when we apply our measuring or any observation or something to it,
But
then
the potential is of something. It's a potential to be something. It's a potential to be matter and energy. It's a potential to be momentum. So if I had completely empty space-time, there's no way of measuring its existence. There's no knowing it without measuring it.
Well, but that's,
That's where the observer
But
comes
that-
in
this-
at a
right.
macroscopic level.
well, this experiment is a la observer, but if it's nilpotent, we can say that there's nothing until we do something to it. And doing something to it entails a measurement apparatus or
Where do
an
you think,
observation.
Peter?
What do I think? Well, I agree with Bosworth on this one. You can't have space without matter. It doesn't mean anything. You can't have matter without space. And nilpotency is the total condition of the universe. It's any object has to cancel itself with the rest of the universe. That's what that means.
I think nilpotency means that in order to have a geometry like a right triangle that is involved with squares, so that you could have a squared plus b squared minus h squared, h, the hypotenuse squared, equals 0, then that, when you reduce that equation to a, b, and c, then you get a complex equation. You get an I in there, but that equation is based on a physical measurement of reality. The structure of reality has to demand, like, to make a triangle, it can't be just an abstract concept. There has to be a concept of something that triggers that ability to measure and make sure it is a right triangle.
To put it another way, if you think of a universe prior to an awareness or an observation, then there's no distinction. It's like the nilpotent background.
Right.
But when a distinction comes forth, then there's the awareness, the matter, the energy, space and time, an entire event universe has occurred there. It isn't like you can just do it abstractly, like you can think up the empty set as a mathematician. But,
That's right, you can think of the empty set, but is there a parallel between that mathematics and an actual reality? And I
well,
say,
there is if you include the brackets and all the background that actually created the bag that is the empty bag.
yeah.
And you, in the process of drawing out that empty set.
Now, I would add one thing to your SAGNAC, is the Dirac vacuum definitely affects the proper solutions to the plasma MHD equations that I show using Feynman graph approaches, that to get the proper conductivity and resistivity of an actual plasma, the vacuum state electron-positron pair production comes in as a series of Feynman graphs to get the right answer. So to me, plasmas intrinsically and explicitly prove the existence of a vacuum, a Dirac type vacuum. And so that's another area besides the double laser experiment and the SAGNAC experiment that's going to the actual measurement of the qualities and quantities of the vacuum state.
I don't see this as a conflict per se. I think the way I've stated it has left out this background, because whenever in the lineage of this you decide to do whatever it is I've been saying for us to do, whether you have to add this nature of background definitions of the nature of the universe, it's still okay. I can move that up to the point when we're going to perform this action. I think these same hierarchical principles already apply at that point. But I think this is of critical importance to, especially from the physicist's point of view, to have that put into the picture. But would you then agree that if I move back or up what I was saying in the context that you just made, that it still relates in the same way?
I think I'm really more talking about terminology, and I think that's what Lou's talking about, more terminology than physics here. And I would say the one question Lou asked, I think the least action or the least unit probably is more like a Planckian unit. But what do you see it as? I mean, what do you picture how that relates to relativity and particle physics. What is that?
It's a Planckian unit in the standard cosmological model, but it is not in this Ham cosmology. And it's not a Planckian unit in string theory. We add string tension. It's Planck plus string tension. So we already have a long precedent for something beyond the Planck unit. But in the standard cosmological model, yes, it stays at Planck. In 4 dimensions, it stays at Planck. But when I add this other hierarchical thing, then it is...
I think Planck's in n dimensions. I think Planck can be extended to n dimensions.
and it can be used to make Planck.
See, I don't think it's in contradiction with what you're saying at all. I think you're making a statement that might be kind of similar, but you do add the string tension point of view that the Planckian model per se, you need some additional components, the string tension plus whatever you're contributing to that concept.
Yeah, so this is a good footnote. In the standard model of a singularity or a vertex, it's rigid, it's fixed. The asymptotic continuous state to the reduction to asymptotic Planck means we have the Witten vertex, which is able to wiggle. So we don't get to Planck. We get down to Planck plus string tension. As I mentioned, current string theory has a fixed string tension, which I drew the little Planck and then a small circle for the addition. But in this model, it goes back to the original hadronic form where string tension is variable. That allows us to get that adds to the released unit rotation, so we get near asymptotic Planck, and at the Riemann sphere topology of it flips back to infinity. The reason for the Riemann sphere going from 0 to infinity is this compactification process from 12 dimensions down to 0, and that's an essential part of the least unit. We need the 12 dimensions, as I said, to surmount uncertainty and to have the whole hierarchy where all this, so it's a new view of reality beyond what we observe.
Can I ask a question?
Yeah.
When you draw the triplet for the least unit, why choose 3? Is that because of the Witten vertex?
It's also, you can see how much Peter, to be silly, I'll say worship the threefold symmetry. That's so a fermionic vertex. So that's the starting point, is a quaternion vertex, the 3 ijk or xyz.
Oh yeah, I got what you're saying, but is there any way?
Well, but
then you could jump to quarks because the SU3 works so well that maybe there's some reason that there's another scale up to get the particle physics at another hyperdimensional compactification cycle that 3 shows up as the 3 quarks.
if we're, and that's probably why the reason for it. As we develop tools of unified field mechanics, then yes, we'll start to be able to play with quarks. So I modeled that conceptually. I made the vertex. Some of the pictures I have the standard vertex that's fixed. Then I put the Witten vertex in the middle of it, which can wiggle. And then I put between, in the cavity, if you talk about a brain, I talk about in the topology, brain, I'm sorry, I forget the term that I wanted to use, but topological charge. So in the Calabi-Yau space, the cavity of the topology can have some charge in it. So the circles, and I said I derived them conceptually from the Broglie-Bohm quantum potential pilot wave. So they're control factors, because this isn't a random evolution. Those control factors guide. I said there was inherent synchronization backbone. Those control factors of the symmetry guide that and keep this in symmetry going. So
Dr.
Control factors of what?
Kramer, that goes in there, Kramer Wheeler.
adding Kramer and de Broglie-Bohm contribution, extending to higher dimensions Kramer and de Broglie-Bohm, you have with the superluminal boost from time to energy, those become control factors governing the evolution of this topology. through,
It's too much at once for me. De Broglie-Bohm to me is, you know, looking at the Schrodinger evolution in terms of something like a pilot wave or an on-local potential. That's one thing. Kramer is a way of understanding the Brockett formalism by thinking a handshake between future and past, and is much more somehow formal, general, conceptual, not tied to the intricacies of the Schrodinger equation of the derivative. So you're speaking in one breath, and and it confuses me.
Calabi-Yau mirror symmetry in 6-9 dimensions has a left-right symmetry. And to me, that's a cap on Kramer is a standard 4 dimensions. That builds a tower on the left-right. The present as a standing wave of the future past. To me, you can just hook that in, and I haven't rigorously defined it yet, with Calabi-Yau mirror symmetry. You can, because of the annihilation creation of the...
But wait, let's slow down again. Calabi-Yau mirror symmetry is about the fact that different Calabi-Yau manifolds act symmetrically with respect to one another, so that parameters in one turn into, like by a Laplace transform kind of thing, into other parameters in the other one, and you get a perfect match. But you're in two different Calabi-Yau manifolds, each of which is its own string theory in the usual sense.
Yeah.
You have some kind of dynamism which would put them together. In your theory, they would be interacting with one another.
Right, exactly. So I give them, that's one of the whole things where I in a sense, criticize Elizabeth's 8 space that it was still reduced to plane. It doesn't have that type of dynamism that kind of exists until you get this continuous state cycle, so that they, and we do know that they will transform it one to another. That's string theory.
Well, I will have to say that I also have a 12-dimensional space, but the point really was with the complex 8 space, what is the least number of additional dimensions do you need to be Lorentz and Poincare invariant that would accommodate non-locality? So the conditions on which I made on the manifold are not restrictive of your conditions.
Right.
Because I also make in that superluminal boost paper a 12-dimensional space, which is certainly possible. It's just that I wanted to have the least number of added physics to get what I wanted. But I have also a 10 and a 12-dimensional space, so it isn't restricted to that.
No, and I realize that, but I just add again this twist. As you recall, we go past Lorentz transformation. We now have a new transformation, so you need a 12-dimensional space to have a 12-dimensional transformation. So the Lorentz invariance is still another stepping stone. So I don't claim that this is rigorous yet, but I stick Calabi-Yau mirror symmetry on top of Kramer and give it. I think I've read enough string theory papers.
Wait, sorry, slow you down again, but what do you mean by on top of Kramer? Kramer says a quantum event is a handshake between the present and the past. You can kind of grasp that better than almost anything else.
Right.
And then you say on top of Kramer we'll put the mirrors, the Calabi-Yau mirror symmetry. What is on top of it?
Do we call it a manifold? Kramer is in.
How about the word addition to rather than on top of?
Yeah, I mean, I think of it on top as it going up the ladder of dimensions, but Kramer is in 4 dimensions, and he has that symmetry, and then I tack on.
Oh, you're thinking past future is a kind of symmetry.
Yeah, same.
Right.
So it
Yeah,
has.
all right.
I add those, and I realize that I have now, especially that I've skipped all that, but so I take the Kramer future past symmetry, and then whether typical string theorists do it in that way. I know I've seen where they can transform all of the 5 models of string theory, cycle them. So I don't see that there's a problem. So I tack on 9 more dimensions to give the Calabi-Yau left-right mirror symmetry the same properties. And that again is essential to the continuous state.
So you have new events that are hand-clasped between mirror symmetric string theories.
Yeah.
When he says above or hierarchy, he really means in addition to, like I'm expanding the space of domain of action that I'm considering exists, which means that he's expanding it to a higher hyperdimensional
Exactly.
geometry above and beyond the Kramer or the Calabi-Yau space, I think.
So that's important to these definitions. So
Can we throw this discussion open?
any
to other
any
people?
questions or comments?
Been very restricted at the moment.
Yeah, it sounds to me like your
Well,
least
that's the
cosmological unit could be, and this is very naive because I don't have,
Just speak up.
90% of the terms you're throwing out here are
Doesn't matter.
like you kind of detached from my knowledge or something. But it sounds like, and I do know Kafatos, I know him personally, but you know, that you're talking about little quantized chunks of space. So I can visualize it as tiny little things. And it sounds as though you're thinking that if there are these multiple dimensions, you may be able, through some oscillations, to tear those chunks apart, and there'll be holes in space. And something will fall
Actually,
into-
only the lower ones are quantized. Once you get the tip of that iceberg in 4 space is quantized at
Yeah,
some
well,
point,
I don't-
then it's not
I'm
quantized
I'm
anymore.
not,
Okay.
I don't know about those higher dimensions. I'm just saying, you know, right now it sounds like I can visualize a couple of little points, you know. Now, when I do this, obviously it's 10 to the, 30th times bigger, right? But, you know, we're physicists, so what the hell. And what you're kind of saying is that these things can be split apart, and there's a hole. How a hole in space, that I think is you're explaining through these higher dimensions, there's a hole in core
Interference.
space.
You know,
And
destructive
something can
interference.
fall in or generate energy, which will, my question now is, it looks as though the experimental setup that you've shown is very much like nuclear magnetic resonance. So how do you get from that experimental setup to anything like the frequencies that would do the thing that you're talking about? I mean, it seems like there would be tremendous energies required for doing that, and oscillations of the kind that are accessible to us may just show us nuclear magnetic resonance again. What kind of energies are you talking about in these oscillations?
I think they're very, very high energy. You'd have to go bigger than the Planckian because the energy for a Planckian unit is very large to mass of 10 to the minus 5 grams. Forget what the energy is, but the Planck energy to get to such a small quantized or discreteness in the space-time manifold would require definitely greater than the LEC.
Right, so
This is a
that's my
beautiful-
question. I mean,
This is a beautiful question. I'm so glad it was asked.
Well, maybe you want to use them.
Okay. Because I hadn't thought of this, giving that answer in this way. De Broglie matter waves. All we've done so far is find out 100 ways to demonstrate that de Broglie matter waves exist. And we haven't done anything else. This is, in a sense, starting to do something else. So instead, we're just using low energy RF pulses, and that's all that's needed. If you couple the resonance right, because of the nature, because of the unified field mechanical nature of matter and its creation and annihilation in this structure, and this will also be an end to supercolliders. We don't need colliders anymore, because with this method, once we can access this manifold of uncertainty, which needs more definition, we'll do a kind of cross-section through this that we'll be able to see the whole structure so much more easily. But the Sagnac effect resonance hierarchy will just use sufficient energy. And it's almost like an NMR experiment, except it's not applied to what NMR is, and we don't need a big magnet. It'll be electron resonance in normal RF compatible with that, those attributes, small
So
tabletop
it's really
energy.
my plasma physics
I
experiment.
don't even know your plans.
I would have
I
to
know I'm describing.
ask what Kauffman said, which is, slow down, wait a minute here, but
I'm going to ask a really difficult question. Very simple question, but extremely difficult. What is your attitude to Occam's razor? Because my attitude is that I go for the least assumptions I can conceivably make about anything. But what is your attitude to it?
This, I see no conflict with Occam's razor because this is the minimum number of parameters that are required to go from, I mean, you can look, you could give that argument if you were a Newtonian classical mechanicist and try to throw out quantum theory.
No, I mean that you have many aspects to this model, and you need them all to work at once to get the model to work.
Well, the big part, remember I said the Feynman synchronization background is inherent, it's half of it's already given to us for free. So that's already all working, all we have to do is do our little RF pulse.
I'm not talking about the experiment, I'm talking about the whole model. The whole model has got many different aspects, which are not conventional physics. Some of them are, but a lot of them aren't. So how do you be sure that putting them all together is going to get a coherent story?
Well, we have an experiment to test it, we're going to do put them all together. But I mean, I see no conflict with Occam's razor because I'm talking about this as a whole cosmology. Of course, there's practically infinite.
But I'm saying, the normal procedure is to test one little bit at a time and see if that little bit fits in, and then another bit, and another bit. If you build a whole superstructure, how can you test that?
This is a flaw in my personality. I have always felt, no, I'm serious. In my personality, the way of trying to describe things, I feel that unless I talk about Ham cosmology, the continuous state, and the least units, and the reduction of the nobody, I felt that the only way that people need to understand it conceptually first. But we could just go straight to talking about the direct polarized resonance.
What I'm saying is that if you want somebody to test something by experiment, you have to put it in the form where you're not actually doing that much more than conventional physics as it now stands.
This is for us.
That.
This is for us.
Okay.
When we do the experiment, it's the same like when we talk about when we want to try to do a paper for science or nature. When we write the exact, none of this, 99% of this cannot go in.
Can I make some comments and maybe break this mood? Yeah, we need that, do I need it? I mean,
No, not necessarily.
Yeah, well, it's good, I'm hard of hearing and I appreciate it. I was gonna say, at least I find, I have too many gaps in my background to compile the motivation for this experiment. So, let's start at the back. If the experiment is supposed to produce a spectral line, that seems to me, it must indicate that you imagine that there are some states between which an electron can do a transition. And evidently, at least half of those states are states that thus far have never been found in, say, hydrogen or titanium or whatever. So there's some states, and I find that a very plausible possibility. At least there are some metastable states or some transient states that might not have been found with conventional means of spectroscopy. Now, if there are some unconventional states, however we get there, with collaborative backgrounds and da-da-da-da-da-da-da, if there are some, then the experiment ought to be able to somehow or another tickle them. And so the question in my mind is, perhaps we should address just how could we tickle whatever kind of states they are that's new and different from the way that states have tried to have been tickled in the past. I find it probably very improbable that a tabletop energy level experiment hasn't been tried already. Most of those, every cheap experiment has been tried by somebody and maybe not reported because it didn't turn out anything new. So you're fishing in very muddy waters.
No, like I said,
But that's not a criticism, that's just a warning.
my cosmology may be a heresy, but I've tried to point out very pointedly that this is only plausible in this cosmology. So
The idea that any physical effect has one and only one explanation is very, there's usually at least hundreds of even maybe incorrect but plausible sounding explanation. But the problem usually with an experiment is to ensure that what you're proving is actually what you're
I'm not
trying to
talking
prove.
about
You can prove
the
all kinds of-
explanation, I'm talking about the context. We do the Stern-Gerlach experiment in a certain context. You can't do it with water waves or some other stuff. The Stern-Gerlach, we send a signal out on the z-axis with a certain frequencies or setup, and it splits into the...
The whole field of quantum optics nowadays does, I don't know, versions of a Stern-Gerlach experiment in construction. That is, in its conceptual construction, there are parallels. They're done optically now.
Right, so
I
this
argue
is
that's
the first.
incorrect.
This is the first experiment along that avenue. But you need.
But it's still,
you need
it's
an
still an
apparatus.
atomic physics experiment. You're still looking for a spectral line. So at the end of the
We've
day,
been looking for those spectral lines for the last 100 or 200 years. We're not going to find any more spectral lines in four-dimensional quantum mechanics.
well, the experiment's going to be done in a.
No, the experiment is
You
just
find them in the
now,
lab.
In the lab.
Oh, yeah, of course. Thank you.
Yeah, I mean, that's,
Yeah,
but that's,
Who has the 10-dimensional lab?
well, I think,
Anybody who
I
wants to
think a
build a
yogi,
Sorry?
a meditative yogi might have a 10-dimensional lab.
Yeah, well, if you smoke the right stuff,
Yeah,
I'm sure.
but,
we'll-
you know, or if you
I'm
smoke
sure I can get there
stuff,
from you.
yes. Yes, you can get to 10 dimensions, but I don't know how many experiments you can do in that state.
Good beer will get you a couple of those dimensions too.
but yeah, I mean, the experiment will either be successful or not. I mean,
Yeah.
and you don't need to include all this to say,
Right.
this experiment might be worth testing. And just do
Let
the
me
experiment.
Let me defend Richard on this a
Yeah.
little bit. Yes, he's getting, by his model, he's getting a different slant on how to modify a Stern-Gerlach type experiment that might look at the real space-time physical reality in such a different way. By the design of the experiment itself, that might find some new spectral lines, just because of his conceptual ideas creating this new direction.
Well, personal motivation is one thing, but if you're going to then back up the observations from an experiment, say they prove your personal motivation, you really have to have a very well-specified line of reasoning that the main purpose of which is to exclude all the other alternatives.
Right, right.
And getting there from here, as Peter's trying to point out, if you have a theory, a motivation with many, many new hypothetical inputs, it's overly. I'm uncomfortable with it. I think like what Peter was saying, if you add one extra hypothetical input to already done stuff, then the experiments will test that hypothesis. But if you add 17, then you've got
You can't
17
test them all.
factorial new.
Yeah, it's not possible.
Yeah.
Well, I think that's a little off the point. It's true I've been talking about a forest, but ultimately when we do the experiment, we'll pull out one tree out of that forest.
Yeah, but you'll only prove one tree, and you'll still not prove your forest.
You have to prove that all the other trees couldn't get there too.
I think it'll be, if this model has any basis in reality, the first spectral line will be easy to find.
So in that case, you will disprove your model if we don't find it.
Yeah.
Is that the way you want to think about it?
Oh, you have to.
He won't
You have to.
disprove it, he'll prove that he didn't find the spectral line. But that never precludes a theory,
I see.
because you might not have looked at it right.
Yeah, I might have done an experiment wrong.
So it really has to
Need
do
two
with
more
the whole
votes.
logic of
Exactly.
experiment
Well, that's why I think
theory.
the other spectral lines will be more difficult. Those will be,
But I'm saying,
That makes it even worse.
you won't sell any idea to the scientific community as it is, unless it's basically based on minimal assumptions. If it's based on a lot, then you'll never sell it, never.
And a
That's
lot
what
of
you
these
guys
ideas,
are
a
for.
lot of these ideas are really shaky When you start talking
But it won't sell everything, Danny, on which it was based.
course not. You gotta
Kramer is
start-
a
you gotta
really,
start
that's
somewhere.
wild stuff, huh? I mean, you're introducing backwards action in time and all.
It's not just minimal assumptions, it's minimal number of different models. Pick a model instead of Kramer and Blaviau and five-dimensional and eight-dimensional, all these. Pick a single model.
as I said, I have
sense.
always felt, it's inherent in my stupidity or whatever, that I feel the need, I don't know where it comes from, to try to explain every complete picture conceptually.
Yeah.
But after that, you can throw out this whole forest except for one tree. And so I could have, as I said, I don't see how I could have got away with it if I just came and started talking about the experiment. It's true, I could have got out all of Dubois' mathematics for the incursive oscillator, the Sagnac effect, and Dirac vacuum, and gone there, but it's still, why should I find a spectral line under those circumstances? I'm only finding a spectral line if there's some additional cavity that opens up behind the manifold of uncertainty. And to say something about that, I think we can find a way of minimalizing that discussion.
But you've got to actually put that in such a way that you give the minimal assumptions needed to find that particular thing.
Well, that's what you guys are before. My talent is to come up with a fairy tale.
Yeah, it's not our theory, it's yours.
I never
But we don't have to convince anybody, you do.
Can that spectral line be predicted beforehand by calculation?
Yes, and I said I start with a simplistic formula for the volume of hypersphere in higher dimensional, the volume of higher dimensional hyperspheres. We get.
What you have to do is extract out that one component that causes this spectral line to exist.
Yes.
And if you can do that, then you can actually maybe get a paper that somebody else can do the experiment, or you can do the experiment yourself, can follow and actually test it out.
So let's go back to the beginning in a sense. So could I take Chandler's titanium experiment and say, if we do this in some kind of a Kaluza-Klein space, what does
that mean? We're going to do it in the lab, not Kaluza-Klein space.
Well, if we can actually do the theory in some Kaluza-Klein space, develop a new piece of information from it.
Okay.
I'll buy that, yeah.
So I'll say it is our guess or whatever that the reason Chandler got a bigger QED artifact is because there is something.
You could sell that argument if you did it as Kaluza-Klein, because Kaluza-Klein is quite respectable, so you could put that in.
Well, so that's fine.
One of the consequences of using it would be this. Could we test it out? You could sell that, certainly.
Because as we talked with Elizabeth, and I kind of went back and forth, that all the spectral lines are measured in 3 space. So if we talk about a 5th dimension,
yeah, that's all right.
Kaluza-Klein space, and say we want to make an argument for testing, for increasing the artifact.
It would be a new test of Kaluza-Klein theory as well.
Or some hypothesis connected right
It
from
ties
it.
in to the standard model because the twistor algebra of the Kaluza-Klein geometry is mappable to the spinor calculus of my complex H space, which is